Hello and welcome to today's webinar presented by Delubal Software. Today we'll be working in our structural analysis and design software, RFEM 6. The topic for today's presentation is ASTM E1300-24 insulated glass design in RFEM 6. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office and I'm located in Philadelphia, Pennsylvania. My colleagues Alex Baca and Siska Cho will be your moderators, answering any questions you may have. They're both support engineers, also located in our Philadelphia office. We always want to encourage everyone to ask questions throughout the presentation. You can do so by entering in your question in the GoToWebinar dialog box as shown here. If by chance we don't get to all your questions, we will certainly send you a follow-up email afterwards. So regarding the content over the next hour today, we will immediately begin within our program RFEM 6, also utilizing the glass design add-on for our example today, shown over here on the right-hand side with 3 different glass panels. So we'll talk in detail the difference of the 2D surface versus the 3D solid model types for both laminated and insulated glass, how this will also affect shear coupling between the different layers. For our insulated glass unit, we'll talk a little bit more about climatic loading considerations like altitude, temperature, atmospheric pressure, and we will be running the design checks according to the ASTM code for these panels today. And of course, we'll be taking a look at the detailed analysis and results overview. Now, I did link a previous webinar here where I do go into a little bit more detail with some of the ASTM design checks and a little bit more information that we just certainly won't have time for today. So this will be beneficial to refer back to as well in addition to today's presentation. So with that said, we can go ahead and jump directly into RFEM. So when you do begin a new model, you are presented here with the base data dialog box. The type of model will be in a 3D environment, and under the second tab are the various add-ons that are available, whether you have purchased them or rented them. Now, for today, we're obviously using the base program RFEM 6, but also the glass design add-on will be activated. So this will allow us to build up these layers for either laminated or insulated glass, but also to take the static analysis a step further to carry out the design checks according to the ASTM code. Looking at our third tab here, this is where we define the standards. You'll notice the glass design is set to the ASTM E1300. We also have the German DIN standard available as well. And if you wanted to do a code independent design, so this is just going to look at stresses and compare them to materials, this is also possible within this add-on. When we have the ASTM selected here, it is required that we generate our load combinations according to the ASCE7 glass. Now, this is identical to the ASCE7, but we also want to specify the load duration factor for each load case, which is required in order to carry out the design according to the ASTM. And that will make more sense once we get to the loading within our example today. So now that this information has been defined, we are brought here into the main program RFEM 6. So you can see I have my graphical window here at the center. I have modified my drawing grid in the vertical direction, and every drawing grid point here is spaced at 1 foot. We can always right click down at the bottom here to modify our grid settings. I want to begin immediately by drawing a new surface. So we will specify a new rectangular surface up here within my quick tools. And we do need to assign a thickness to this surface. So we create a new definition type here. The initial dropdown that's presented to me includes the glass composition. And this particular thickness type is only available because I have activated the glass design add-on. Without that add-on, I would not have access to this thickness. So when I select this, I now will visit my second tab here where we can build up the various layers of our glass panel. Now, to begin, I am going to start off with laminated glass. So we will start by selecting our material from our drop-down box here. Now, in this case, I already have the materials defined, but we could always visit our material library if we didn't have any materials in our program yet. And within the material library, we could set the filters over on the left to the United States. We can select here the material type, which is set to glass. And then you can see under the ASTM standard, we have 3 different glass options. Today we'll be utilizing the fully tempered glass. Now, in addition to this, we also have the foil types under the United States with the manufacturer century glass, which again will also be utilizing for our interlayer today. If you do go ahead and clear out the region here, there are some additional options when it comes to foils that you can see selected from this list here. We will also utilize the code independent gas material type once we do get into the insulated glass panel. For this, you can see argon's available, dry air. So likely one of these materials will already exist within our material database. But if for any reason you don't see your material there, you can always select an existing material and set this as user defined to tweak those modifications to the material values themselves. So as mentioned, we already have these materials defined here in my model today. So for my first layer, I am going to select here the fully tempered glass, and the thickness is going to be set at 1/4 inch. And I can input this in either as a fraction or a decimal. The edge finishing is also selected here. So this is either clean cut, seamed, or polished edges. We'll go ahead and choose polished. This does influence the capacity of our glass when it does come to the ASTM design checks. So that's just something to keep in mind. That's why we are setting the edge finishing here. The second layer is going to be that interlayer with a very small thickness of 0.03. And the final layer will be glass, yet again, of 1/4 inch and polished edges. Now, once we have these layers set and you're working with these quite often, you can always save them to your template library. So you can go ahead and give it a name. And then for every future RFEM model, you can have your templates available here so that you're not defining these layers each time. So in this case, I only have one template defined, but you could, of course, define as many as you'd like there. That will just be a nice time saver again if you're working with these same layers over and over. So once we have defined this thickness, it is assigned to this surface, and then we can graphically draw this particular surface. So I'm going to snap at the origin point here, and I'm going to click on my second point, a width of 4 feet and a height of 8 feet. Now, one other thing just to pay careful attention to when it comes to the thickness is that when we look at the local z-axis here, we want to ensure that this is oriented properly with my surface back in the global model. In this case, this is a pretty symmetric layout here, so it really won't matter in which direction this is oriented, but for unsymmetric compositions here for glass, we would want to pay careful attention to that. So now that this surface has been drawn, we want to apply some additional supports. And to begin, I'm going to apply line supports to the boundary edges here of my glass panel. There are many different ways to work in the program. I can select here a new line support, or we can go ahead and apply it through the navigator on the left under types for lines. You'll see that expanded here. Utilizing my quick tools up at the top, I will create a new definition type. And the first line support here that I want to define will be supported in the out of plane X direction only for translation. But I don't want a fully fixed support. I don't want it fully released, but somewhere in between. So we'll go ahead and specify a spring constant of 40 kips per square foot. I click OK. And then once I am back in this initial dialog box, I can graphically select all of my boundary line elements for this surface. And I can go ahead and click OK. So you'll notice that the line supports are now shown. If we right click, we can also take advantage of this slider to decrease or increase the size. That's the true for all support options within RFEM. We also want to apply a couple nodal supports at the base of this panel. So we'll begin first with the nodal support on the left by creating here a new nodal support definition. I create a new definition type, and for this first entry, I want to support it in the global Y and Z directions only. So I'll go ahead and turn off the translation in the X and also the rotation here. I click OK, and then I can graphically select here node number 1. When I click OK, I have the ability to hit apply within this dialog box. So we see that nodal support applied to node number 1, but I still remain in this dialog box where I can create a second definition here. And for my second nodal support on the right-hand side, this will just be supported in the vertical Z direction only. All other degrees of freedom will be released. I click OK. I'm going to graphically select here node number 2, and I click OK through these dialog boxes, and that second nodal support is modeled here. So the first surface for our laminated glass panel is complete. I'm going to use my selection box here to highlight all elements graphically. And when I hold down my control key on my keyboard, I have the ability here to quickly make a copy for my second surface. And then I'm going to do the exact same thing again, a third time here for my final glass panel. Now, as we have it modeled here, all three of these panels are identical. But what we would like to do is to assign different thicknesses here for panels 2 and 3. So I can double click on panel 2. And again, that original thickness is currently assigned. Let's go in and edit this thickness where I can make a copy of the existing laminated glass layers here. And you might be wondering, why am I making an exact copy? This will make more sense as we move through our example today, but more or less it is going to be exactly the same as panel 1. I need to select here my second thickness that I've just defined, and I click OK. We're going to do the same thing for panel number 3, where we're going to go in and edit the thickness, but this time I'm going to create a new definition. We're going to select here the thickness type from the drop down to glass composition, and under my layers tab, this is where we want to create the layers for our insulated glass unit. So I'm going to select here my glass material. The thickness will yet again be 0.25 inches or 1/4 inch. We will select polished edges. The second layer is going to be that dry air material that I've already populated here within the RFEM model. So this thickness is going to be 0.5 inches, and then we need to place another glass layer on the other side of our gas. This will be 0.25 inches, polished edges. And we have the ability with the layers here to not only define laminated or insulated, but also to combine the two. And that's what I'm going to do for this last thickness as well, to select my interlayer at 0.03 inches, and my final and fifth layer will be glass once again at 0.25 inches and with polished edges. So you can see how it will be advantageous to take advantage of your templates and saving them to your library in order to not define this over and over again. Now, this would be an instance too where we want to pay careful attention to the local Z axis since we have an unsymmetric layout here. So now that we have defined this third thickness type, we need to ensure here that that is selected within our dropdown and assigned to panel number 3. So the modeling is essentially done for these 3 different types. Remember, laminated, and insulated. So I'm going to go back to the navigator over on the left, and I'm going to right click to collapse all these folders. If you find all the different options a little overwhelming, you can always collapse these folders at once, which is a little bit more able to navigate here. We'll start off with the glass design folder. Again, this is only available because that glass design add-on is enabled. And under this folder, we have here the different glass composition models. So the glass compositions, I'll go ahead and edit these, are created for our glass surfaces. And a separate composition is always created for different thicknesses or different geometries. So if I had left the same thickness defined for all three of these panels and all three of the geometry is identical, then I would see only here one composition. But in this case, remember, I have three different thicknesses defined, even though the geometry is the same. So therefore, I have three different composition models. Now, we'll go through this in detail. So starting off with the first composition here assigned to our first surface, we want to set the modeling type here to a surface model. And we're going to get into more detail with this in just a minute, but this is also where we are going to set either coupled or uncoupled for our shear coupling between those layers. Now, the second composition, and we'll go ahead and actually click apply here. What we should see is that this composition will turn black here in the background. Red typically means we need to address something, so we'll talk about what that means in just a minute. The second composition is assigned to panel number 2 here. Remember, this is identical to the first one, but for this case, I'm going to set the modeling type to a solid model. And I'm going to go ahead and click apply. What we will see here is that for the second composition, the reason why it turned red here is because the program says, hey, wait a minute, we need to go ahead and orient the local axes of the lines if we're going to generate these solid elements. So we have a quick option here just to tell the program to go ahead and do so. Now, the third composition here is going to be assigned to our third panel, and this will also be a solid model. So for any one of these particular solid models, we'll ensure that the rotation is set. We should be able to click OK, and then now we see all three of those compositions look okay. So let us talk a little bit more about the surface versus solid model here, as well as shear coupling. And we'll go ahead and refer back to the PowerPoint. With the surface model, this essentially is a 2D object in RFEM, which is an FEA program. And we're going to keep that glass panel as a two-dimensional element, but we have two different options here when it comes to shear coupling. The first is a 2D element, a surface model with rigid shear coupling. So this is essentially where all of our layers are rigidly connected together. So therefore, we're going to get rigid shear transfer between each one of those layers. Now, the alternative option with a 2D surface model is to have essentially an uncoupled option where we have free shear coupling. The layers are allowed to slide independently, and we're not going to have any shear transfer between those glass panels or those glass surfaces to the inner layer surfaces. So those are the two different options here when it comes to that surface model, either fully rigid or fully released. Now, alternatively, we have the 3D solid model. So we're now introducing this third dimension, this solid object, into this FEA program for our glass structure. And for this, we will actually consider the true shear coupling between each layer. The inner layer, such as our foil or our resin, the material properties will be accurately considered for accurate shear transfer between the glass to the foil or resin, and then also to the glass as well. Now, this does require a large deformation analysis. So this is third order analysis. The program will automatically detect this. And although we're getting accurate shear results, accurate shear transfer results, just keep in mind it will take longer calculation times than what we see with the 2D surface model. So now we might be wondering, well, when am I supposed to use a surface model versus a solid model? So we'll go ahead and cover that on this next slide here. We have some recommendations for the model type for three different glass structure types. And we begin with first single layer glass. So this is obviously the simplest composition. We just have a single glass layer. And for this, in most cases, probably a 2D surface would be completely sufficient because we don't really have to worry about that shear coupling with only one layer. However, if we are starting to see the thickness over length ratio greater than 0.05, then that plate theory is no longer valid and we need to move to solid elements, so three-dimensional objects here. So therefore, solids are recommended for thick plates, and this is really true for all glass structure types. So whether it's single layer or laminated, we would recommend moving to a solid if that thickness starts to really increase in comparison to the length of our panel. The second type is laminated glass. So this is essentially where we have two or more glass panes with this inner layer, this foil or resin. And for this, either 2D or 3D is possible. So keep in mind with the 2D, as we discussed on the previous slide, it is either fully rigid shear coupling or fully released. It certainly could be possible that you run this 2D surface model without shear coupling for long-term loads where the shear resistance of that inner layer should not be considered. Now, alternatively, would want to move to a 3D solid if we have significant shear distortion. So this might occur when our glass thickness and shear modulus is much greater than the foil thickness and shear modulus. So as we mentioned on the previous slide, we're going to get better accuracy here, but it's a compromise of a little bit longer calculation times. Of course, if you're just running a few surfaces or panels. With the solid model, the calculation time won't be too long depending on how many load combinations you are considering. So the third type is going to be insulated glass. And this is essentially where we have layers that include the glass panes. We also have a gas layer and then possibly inner layers such as that foil or resin again. And for this is always 3D modeling. We have no other option to run a 2D surface element. We always have to run with these three-dimensional solid objects. And this is because that gas layer is modeled as a solid where the ideal gas law is applied. Now, we also have the ability to define in RFEM the spacer and seal properties for the gas solid end conditions. We'll talk about this a little bit later on in the PowerPoint as well. And finally, when we have something like insulated glass, we typically want to take into consideration climatic loads. So this is altitude, temperature, and atmospheric pressure differences. Now, unfortunately, when we refer to the ASTM and other US codes, there's really not a whole lot of information about these climatic loads for insulated glass. But when we refer to the German standard, the DIN code here, this does include detailed climatic loading. And this is the approach that we have taken in RFEM 6, even when you are designing to the ASTM standard. I have also linked here an additional resource that talks quite a bit about climatic loading that RFEM 6 also may more or less follow. For those of us not familiar with or not fluent in German, you will need to translate this. It is a PDF document entirely in German, but this could also be helpful for those of you wanting to learn more about the climatic loading. Okay, so what we'll do now is to go back into RFEM to, again, take a little bit of a detailed look at these compositions. So now that we understand the surface versus solid model in a little bit more detail, again, we're looking at this composition number 1 here for our laminated glass that is set to a surface model, so a two-dimensional object. We can select here whether it is rigid shear coupling or completely uncoupled and free. For this one, I'll go ahead and leave this as coupled. The second tab just reiterates the layers that I've already defined within the thickness. So not too much to discuss here, but you will know that each layer has its own stiffness properties. So we're going to utilize the laminate theory to then calculate the global stiffness matrix here of the panel, the global panel itself back in RFEM. So this is really powerful in the sense that the program's automatically considering all of those layers. We can also display here full transparency what that stiffness matrix is, whether it's coupled or uncoupled. Now, these supports are also given to us here. So we have our line supports, again, just reiterating that those out of plane line supports are applied at all four boundary edges, and also the nodal supports. We have our nodal support on the left and the nodal support on the right. So now that we have covered this first composition, we'll move on to the second. And remember, this is identical to the first, but I did modify it here to a solid model because I thought it might be interesting. Okay, let's compare a 2D surface option to a 3D solid to see how our results differ between the two. When we have this set to a solid model, we do not set any shear coupling because this is automatically considered within the calculation itself according to third order analysis, where we will account for the true shear coupling between those layers. Under the second tab, again, just reiterating those layers, but now that we have moved to a 3D solid, there is a difference here. We need to set what we call the reference plane. And you can see this dark line indicated here graphically is currently set to the top of layer number 1. Well, I'm going to toggle this down to the bottom of layer number 3, and we see that update graphically. So the point of the reference plane is that where do we want by default all loads applied to this three-dimensional object? And also, where do we want all supports to be applied to this three-dimensional object by default? Now, we always have the ability to modify these placements, which we'll be doing so in our example today. But again, we just need some reference point or reference plane in order to initially apply the loads and the supports. So under this third tab, line supports, again, just reiterating here are line supports at the boundary edges, but because we have moved to the solid model, we now have a little bit more control over where we're placing these supports. For this line support, if I do absolutely nothing in here, again, it's going to be applied to that reference plane, which is the bottom of layer number 3. So we'll go ahead and leave that for our line supports. But looking at the nodal supports, this is essentially where I can toggle here to the cross-section view. And I'm going to tell the program to apply the nodal supports at layers 1 and 3. Those are our glass layers. And we want to apply it here at the middle. So now we see this update graphically. We're going to apply that nodal support right there in the middle of those 3D glass solids. Same thing for my support on the right-hand side. We'll go ahead and toggle this to the middle. So again, you can see how we have a little bit more control over the support placement when we have moved to this three-dimensional object. So we're now going to take a look at our third composition for our third panel. And the program has automatically detected that this has a gas layer. So we have no choice here to choose a 2D surface element. Only a solid model is available to me. And shear coupling, same thing. We can't choose any option here because a true shear coupling will be considered within the calculation. Under the layers, I will toggle the reference plane here to the bottom of layer number 5. And looking at the line supports, so I do want to make some adjustments here. I'm looking at a cross-section view of our different layers, and within all of my line supports, I'm going to go ahead and apply this to layers 1, 3, and 5 at the middle. So now we see that line support kind of adjusted here directly to each one of those glass solids. And I'm going to do the same thing for each one of the boundary lines here by selecting layers 1, 3, and 5 within my drop down, and one more time for my final layer. A nice trick here is if I hit the down arrow key and F8, that will go ahead and copy that input setting to all of my additional rows here. So now those are all set to the middle for our glass layers. The nodal supports, we want to make some modifications here. And actually, for my line supports, I'm going to go back and change this to only lines number 1 and 3. So I don't want to apply it to that middle layer. So we'll go ahead and make that modification here and for our last one. Okay, good. So as you can see here, only the external glass solids. Now, under the nodal support, this is where I do want to apply it to all three layers. So 1, 3, and 5, the support location will be the middle, and we have only one other nodal support where I do want to apply it at all three locations. So there we go. So 2 layers for our line support, and then our nodal supports will be all three located in the middle. Now, the final tab here is specific to our insulated glass unit, and this is where we can specify our spacer. Now, you'll notice by default, everything is deactive here. So let us go to the PowerPoint to discuss this in more detail. So this dialog box allows us to not activate any spacer. And in that case, what you'll see here is if we're looking kind of at a plan view of our gas solid, we have our gas solid, and on either side for our boundary edges, we will have our glass solids. The glass is going to be a pretty high stiffness, something like 10,000 KSI. Well, internally in the program, we have to close off the other boundary edges of this gas solid. So we apply a very soft material, something like 1.5 KSI. And for this, so this is the gas solid that we see over here on the right hand side, kind of a zoomed in view. So I'm talking about these very small surfaces here at the top and at the sides. Now, in addition to this, we will apply a side support to restrain the translation. So again, looking at the same view here, we are going to apply these side supports, and that's kind of this green dotted line here all along the edges. So that way, when the gas begins to expand, we're going to see deformation of the glass solids themselves. Now, alternatively, we can go ahead and activate in this dialog box the spacer. And for this, we will define a custom material and thickness. So no longer are we going to use what the program has set for us, but rather we can account for our own material and thickness for the edges of this gas solid. And the side support is optional here, but it's likely going to be deactivated. So in that case, when we remove the side support and we see expansion of our gas solid, we're going to see additional deformation here of the side surfaces, again, that we have specified here for our spacer. So I think it's important to kind of discuss all these different settings here and what's exactly going on in detail within the RFEM model. Now, going back to our model today, we're going to go ahead and leave this as deactive. So again, we're going to apply this side support internally. The program will create this very soft material. Everything will be done automatically. But again, if you want to modify that, you can always activate it here, define a thickness and material. So now that this information is defined for all three compositions, let us go back into RFEM to take a look at what the program has automatically modeled for us. So when I expand my basic objects here, you'll notice under the solids, I have some automatically generated solids that include my glass, that include the gas, and also that inner layer. If I expand out the surfaces, we can see all the surfaces that were also created automatically by the program, denoted by that purple color. Well, when I'm looking graphically here at the model, these just still look like two-dimensional objects to me. So what we would want to do is to take advantage of this button in the upper right-hand corner to display the glass composition model. Now, this is also available here in our dropdown under the View tab at the very bottom to display the glass composition model. So when I activate this, you'll see here that this first surface is again still a two-dimensional object. That's what we have set. But this second panel here is now solid elements. And we can view this by zooming in quite a bit here to view in a bit more detail. And in addition to this, I'm going to go ahead and modify my colors for my solid based on the material type, and we'll go to a solid rendered view. So we have our glass solids in the back. We have our inner layer foil resin layer in between, and then we have our glass solids up front. And you might be wondering, why are there two glass solids? The reason why is because we allow you to place the boundary conditions, the supports, at the midpoint of the solid. So in order to do so, we had to split this up into two separate solids, but the total thickness is still 1/4 of an inch thick. So that's a little bit more about what's going on. And again, it might be interesting to compare this 3D solid to the 2D surface here. Now, looking at our insulated glass unit, as we zoom in, the first thing we notice is that this is a little overwhelming with these line hinges. We can right click here to significantly decrease the size of those. Also, here's those side supports that we talked about in the PowerPoint. We can decrease the size of those as well. So we zoom in here and we have our glass solids in the back. We have our gas solid shown here in green. We have an additional glass solid layer here, inner layer, and additional glass solids. So everything is created automatically by the program. We don't have to manually create these solids. I will say, though, that it is entirely possible, if you don't want to use this simplified surface into these 3D solid options, you can manually create a solid and assign it as a glass or a gas or an inner layer. This is also possible, but certainly taking advantage of the program's modeling abilities will be very efficient. So now that we have taken a look at all of these elements, and also should be known, all the supports are shown here. Again, this 3D solid allows us to get very detailed with our support locations. We don't have any members in today's example, but I can always come up here and draw a new beam member, such as an aluminum mullion, and assign it to the line elements of our solid. So we could do the entire supporting structure along with the glass panel all in one model. And that initial webinar that I linked at the beginning of this PowerPoint does include some additional members being designed with the glass panel. So you can certainly refer to that. Let us quickly take a look at the FE mesh as well. So here in our dropdown, we have the mesh settings. By default, this is set to 1 foot. We probably want to decrease this to something maybe like 0.33 feet. If I click OK and apply, we can quickly generate the mesh just to take a look at what this looks like within the model. As you can see here, our 2D surface element still remains as a two-dimensional object, but our solid elements now have a thickness that is accounted for with this FEA analysis. And maybe the most interesting one is to zoom in here for our insulated glass unit, and we see the FE mesh layered throughout the thickness in the global X direction here as well. So we can turn off the display of our mesh. And the next thing to move on to is loading. So for our load cases and combinations, I'm going to open up that dialog box within RFEM. Remember, we are generating the load combinations automatically according to the ASCE 7 with this glass option activated. And when the combination wizard is checked on here, we automatically generate the load combinations. You can always uncheck this if you prefer to manually create those load combinations instead. Under the load cases, I am going to rename this default load case to dead load. The self weight is automatically accounted for here, and the action category is set to dead load. And notice that the load duration is also set within this dropdown. So we have some assumptions every time you do create a new load case, but you have full control to modify the load duration. Again, this is needed to carry out the ASTM design checks as it does affect capacity. So our second load case, we'll go down here in the lower left to create a new load case definition. This is going to be wind load. And the action category will be set to wind. Notice the load duration updates here. We'll create a third load case. This will be live load with the action category set to live. And my fourth load case will be a bit unique here. So this one is going to be set to a self-straining force variable. And this is going to be for my climatic loading for summer and winter for my insulated glass unit. I am going to modify the load duration here to 3 months, and we want to give it a name. We'll start off with altitude for summer. We will make a copy of this, and instead of altitude, we'll modify this to temperature. And one more copy for summer. This is for the atmospheric pressure. So we can go ahead and abbreviate this for atmospheric pressure, summer. Now, all three of these load cases have been defined here for summer, so we can make an exact copy of them and go ahead and rename these last three for winter. So altitude for winter, temperature for winter, and also we have atmospheric pressure for winter. So now that all of the load cases have been defined, we want to combine them together into the load combinations. And we do so with what's called the design situation. The program will automatically create our factored LRFD load combinations according to the ASCE 7. It will also create the ASD load combinations or unfactored. And this is going to be used for the strength design checks within the glass design add-on. Now for today, I am just going to use ASD or unfactored load combinations for strength. I don't need the LRFD load combination. So I can just simply deactivate them here, or I could completely delete them using this red X. But the ASD will be relevant for strength design. Notice for serviceability, we actually refer to the IBC here to generate these load combinations rather than the ASCE 7. And the reason why is the IBC mentions glass a little bit in more detail. The ASCE 7 really has no mention of glass. So therefore, we're going to generate these load combinations for serviceability or deflection checks within the glass design add-on. Now, the problem here is that when I toggle to my load combinations, the program is going to combine all of those climatic loads for summer and winter together. And this is not correct. We won't have both of those load cases occurring at the same time. So therefore, we can take advantage here of the inclusive exclusive option. So we're going to go ahead and activate this for ASD. And I create a new definition type here under the second tab for exclusive, where I'm going to tell the program to essentially select all of my summer load cases here. And I'll go ahead and move them over to the right-hand side. And I never want to combine with the three winter load cases. So I move those three load cases over to the right-hand side for consideration. So now the program knows never to combine load cases 4 through 6 with load cases 7 through 9. So when I click OK and I jump to the load combinations tab, this looks quite a bit better. We again should see only these summer loads acting along with dead, live, and wind, or winter loads, but never summer and winter together. Now scrolling down to my IBC load combinations, climatic loads are not considered here, only live, wind, and dead, so we don't need to worry about that for this particular design situation. Now, you will notice that everything is run according to a large deformation analysis. We have enabled that solid model for the glass calculation, including that gas layer. So inevitably, we have to run a third order analysis. That's the only option available to us here within the program. So now that the load cases have been defined, we need to actually apply the loads to the structure. So we can use our drop down box here. And for the dead load case, I'm just going to leave this as self weight. No additional loads will be applied. But for wind load, we want to apply a wind pressure to each one of these surfaces. So we'll go ahead and apply a new surface load. But before I do, I'm going to go ahead and turn this back to the simplified view. So again, this just looks like three simple surfaces for all three of these glass models. So creating a new surface load, I want the load direction to be in the global x-axis. The load magnitude here is going to be negative 0.03, and I am going to assign to all three surfaces. So I click OK, and now we see that wind pressure applied. So looking now at our live load, I do want to apply just a simple handrail line load to the third panel. I won't apply any live load to the first two. So for this, we can take advantage of our free line load. So these different free loads allow us to apply loads to different parts of a surface or a solid element without applying it to the entire element itself. So we start with this new free line load, and in this case, we want to apply it in the global YZ plane in the load direction of global X. The load magnitude will be 0.07 kip per feet, and it will be applied here to our simplified surface number 3. Then I just need to select 2 points to apply this line load. So I'm going to snap to a point 3 feet from the base of my panel, and I'm going to snap to the other side of the panel for point number 2. You can see the coordinate points are populated here. I click OK, and now we see that live load applied to this panel. Now, if I turn this into the detailed solid view, if you remember, I talked about that reference plane. And when I double click on this live load, remember it's applied to surface number 3. And I'm going to scroll in here and I notice that surface number 3 is on the wrong side of the panel. This is because that's that reference plane that we talked about. So by default, all loads are automatically applied to this reference plane. Well, I need the load to be applied to the inside of the glass panel. So it's very easy to modify this. I can go ahead and clear out my selection, and instead I'm going to select here surface number 73 and I click OK. So it's important that we have the correct loads acting at the correct location. If we take a step back and take a look at our wind load and I double click here, I take a look at where it's being applied, this particular surface, surface number 3. In this case, that's fine. Our reference plane also corresponds with this outer surface here of the 3D solid. So we ensure that that wind load is applied at the correct location. So no changes are needed here. The final thing to do is to apply our climatic loading. So we're going to go back here to our glass compositions. We can go ahead and right click to edit these, and we want to jump to glass composition number 3. So this is the one with our gas layer, of course. Well, down at the bottom, we have the ability here to enable these climatic loads for summer and also for winter. And now we get 2 additional tabs here at the top. So looking at the summer, we have the ability here to specify specific values or differences for altitude, temperature, and atmospheric pressure. Now, again, referring back to the PowerPoint, as I mentioned, ASTM, not so much information here. So we are referring to the DIN standard, the Eurocode here that is a little bit more clear about what these additional loads should be for insulated glass units. So I have already defined the load cases in my load cases and combinations dialog box. So therefore I can just simply select them here from my dropdown. So we're going to assign load case 4 to altitude, load case 5 to temperature, and also load case 6 to our atmospheric pressure, all for summer. I'm just going to leave all of these values as default for now, but of course you would want to make the necessary changes here for your project design. Exact same concept for winter. We're going to select here my load case number 7 for altitude winter, load case 8 temperature for winter, and finally atmospheric pressure for winter is load case 9. So when this information is now set, I click OK, and the program will actually apply these loads directly to my surface. So if I take a look at my summer loads, again, it's only applicable to my insulated glass unit, but we have a pressure here shown for altitude differences. We have a solid load for our temperature, climatic loading applied directly to the solid element itself rather than a pressure applied to the surface objects. And finally, we have our atmospheric pressure differences shown here graphically as well. So when I toggle down to maybe one of the load combinations that includes all of these, you can see them all graphically displayed. We have our wind loads, our live loads, and our atmospheric pressures all considered graphically here. So we're now ready to move into the design. And what we want to do here is to turn this back to the simplified view. I'm going to select all 3 surfaces. And I can go ahead and double click on these surfaces to edit them. You'll notice that the design properties is activated down here at the bottom. So this just means that not only do I want to carry out the analysis, but also the ASTM design checks within the glass design add-on. If I only wanted analysis, I could go ahead and uncheck this here. We have the design configurations tab available, and here is where we set our strength configurations for all three of these panels. And for this, we are going to check the principal tensile stresses, sigma 1. We also set here the probability of breakage. We can check allowable edge stresses according to the ASTM standard. And this is true for both surfaces and solids. And this is information that I do go into much more detail in the previous webinar. So again, refer to that webinar if you want to revisit this in more detail. One thing to notice though under the solids, so we have our surfaces solid model. That's what we're utilizing today, where we're drawing this simplified surface, but the program's generating all of these solid objects automatically for us. Well, the other option that you see down here is just solids. This is for manually created solids, which we don't have any in our example today. But again, I told you have the ability to create those three-dimensional solid objects and assign it as a glass or gas material. In this case, we cannot check edge stresses, just simply a limitation of the program because we don't know how the geometry is for the solid, but certainly edge stresses will be checked for any solids that are automatically created by the program. The serviceability configuration, this is where we set our limiting deflection ratios. L over 175 is set here for panels supported at both edges, and also L over 50 for cantilevers. Same concept for solids, so you can go ahead and modify that as you see fit. The final tab is the deflection. So is the panel supported at both edges or is it a cantilever? Because we need to know which limiting deflection ratio to refer to. And also, what is our reference length? You can see that this defaults to the minimum boundary line of the surface, in our case, 4 feet, and that's okay, but you can always override this or set it to the maximum boundary line if you'd like. So now that all of this information has been verified, we would jump down here to the glass design add-on, and we have our design situations listed where our ASD load combinations will be set to strength limit state and serviceability. Design situation will be set to serviceability limit state. So we can click on the show results button here to begin our calculation. This does take just a minute, so I will simply toggle over to an already saved model here where the calculation was carried out. So when the calculation is done, we see here the results for both the static analysis and the glass design. So let's take a look first at the static analysis. And for this, we can cycle through the different global deformations here for any of the load combinations and just seeing how this graphically updates here for each one of our panels. We also can view the surface stresses. So in this case, we only have one two-dimensional surface object. Remember that laminated glass. So we can view the stresses here for the principal stresses, sigma 1. And what's really cool is that I can expand this to say, okay, I'd like to view the stresses for layer number 1 or layer number 3. And furthermore, I can specify which layer side, top, middle, or bottom. So a lot of control here over the stress visualization for that two-dimensional surface object. Now, in a similar manner, we also have our stresses for our solid. And for this, we're probably interested also in principal stresses sigma 1. And we can kind of flip this around here as we'd expect. We have higher tensile stresses, likely due to that wind loading or some of those climatic loads at the inside of our glass panel. So you can create different visibilities by different solids to view those stresses. And also, we have the ability here to view the gas pressures. So I can go ahead and activate that. We only have one solid that is a gas material. We can see the relevant pressure here in PSI. And then, of course, all of our reactions are also available to us graphically. All of this information um, is shown in table format as well. So we can jump here to the static analysis if we're interested to view the information by surface or by solid. Perhaps we jump to the solid. Maybe we're looking at the principal stresses. We can export this out to Microsoft Excel at the click of a button for further sorting capabilities. So not only is everything shown graphically, but of course also in table format. So now we want to toggle to the glass design results. So we've taken the static analysis and now we're applying the ASTM code design checks for each one of these elements. So when you are done running the calculation, you may get some different warnings here. And these warnings are pretty self-explanatory in the sense that, hey, we can't design a gas solid type, or we can't design the inner layer solid types. That's totally fine. We're only designing the glass solid type. So that's just what these errors are referring to. Then we can toggle here to the design ratios on surfaces or solids. So we'll begin first with the surface element, and we can maybe turn off the display of the solids. So again, we have this first laminated surface. We are getting results here for our principal tensile stresses as well as our serviceability checks. And in this case, serviceability is controlling with the design ratio of 0.76. But maybe looking at the design check details for the principal tensile stresses, we can zoom in here. And we can see what is the demand stress from the analysis versus the allowable stress from the ASTM code. So depending on where we're at with this particular panel, we might be checking edge stresses, again, around the edges, or just general allowable stress here towards the center of the panel. So toggling now to the design ratios on the solids, we can take a look at the design ratios of each one of these solids. We can go ahead and update them graphically, shown here too. By the way, you can view the values on the surfaces here. So this is currently set to show each value at every FE mesh point. And when we take a look at the design ratios by solid, so you'll notice that, again, we're checking those principal stresses, sigma 1. We're also checking deflections, very similar to the surface element. And what else is cool is that in addition to the design check details, we can view the results diagram here, kind of looking at a cross-section view. And actually, I'm going to toggle down to maybe one of my insulated glass because this might be a little bit more interesting for us. So again, we have that glass layer, that gas layer, and then glass, inner layer, glass. So we can use our drop down here to view the stresses. These are going to be sigma 1, those tensile stresses, as a cross-section view at this particular point here where that red arrow is pointing to. You can also toggle here to the shear stresses. So again, we're accounting for the true shear coupling behavior between each one of these elements when we have moved to this 3D solid object. In turn, if we were to look at this shear transfer for the 2D surface, we would see either rigid coupling or fully released. So that is just a general overview here of the differences between laminated, insulated glass, but especially this new solid type within RFEM 6 that we would always use for insulated glass. But again, we could also utilize a solid for laminated glass, which again, you could kind of compare the results here for a 2D surface versus the 3D solid for the exact same thickness types. All right, so we are nearing the end of our presentation today, so we'll go ahead and turn it back to the PowerPoint here to wrap up. So if you're interested in what you saw today, either for glass design or any other capability that RFEM 6 has, and you're interested in maybe testing it out in the 90-day trial version, or you want to have a chat with us, we would certainly encourage you to reach out to our team here in Philadelphia. Our contact information is shown here at the bottom of the screen, including our email address, info-us@delubal.com. You can also scan this QR code in the PowerPoint that's included within the GoToWebinar here. That will take you to our website to fill out the online form, and we'll certainly reach out to you from there. So we will have many more upcoming webinars. We try and hold these approximately once per month. You can register at delubal.com. Under support training webinars, as most of you know, I tend to send out a couple reminder emails before these take place, so you can also register directly through the next upcoming email. PDH certificates will automatically be emailed to all participants who are here for the full presentation. This is a requirement of the states that we are pre-approved providers that you are here for the full 60-minute duration in order to receive that PDH. If you watched in a conference type setting or you watched with a colleague and you yourself did not register for this go-to webinar, but you were here for the full duration and are wanting PDH, you will need to request that at the email address shown here, info-us@delubal.com. Just go ahead and let us know who you watched it with, again, ensuring you were here for the full duration, and we'll be happy to issue that PDH certificate if you yourself did not register for GoToWebinar. The final thing to mention is just a fun little contest that we're currently running. So any of our customers that are joining us today and you've carried out some type of project design, either in RFEM or our Wind, go ahead and submit that project here by scanning this QR code that will take you directly to the website. We made this incredibly easy. You just need to upload a few details about the project, and we are giving out a cash prize for first, second, and third place. The deadline for this is Tuesday of next week, so only a few days left. Again, we'd really encourage you to participate in this, and would love to see those projects where you have used Delubal software. With that said, I do want to thank everyone for attending. There will be a short survey that pops up. We'd love to hear your thoughts about this webinar and any other feedback that you have. And as always, we hope to see you at the next presentation. Thank you.